Hey guys, so I want to start off by going through the assignment questions, find the following and draw what it looks like in the diagram. So I'll start off by drawing. So this is reflection, and this is a normal line right here. So reflection is just when it bounces off the surface, stays in the medium, and angle 1 is equal to angle 2. So it bounces off the surface, stays in the same medium. Refraction is when a light, here's the normal line, is when a light beam comes in and then it enters a new medium, and this angle here and this angle here, so this is 1 and 2. So angle 1 does not equal angle 2. That's what refraction is. So light comes in, goes into a new medium, and it bends as it goes into a new medium. Diffraction is when light goes, or waves go through an opening, and as they go through this opening here, they bend as they enter that opening. And polarization is when we have our polarizing filter, and we take another polarizing filter. So when the light comes in here, half the light is blocked out, and the same half would be blocked out, so this would let half the light through. But if we rotate this 90 degrees, then it would block out all of the light. What's the main difference between a refracting telescope and a reflecting telescope? Well, refracting uses lenses, and reflecting uses mirrors. Those are very key to what you know. Okay, and that's it. Easy assignment. So let's go through these sample diploma questions now. Oops. There we go. So in the diagram above, the path of reflected light is labeled and the refracted light is labeled. So reflected light has to be the same angle, and that's going to be Q. So Q is the same one, and then the refracted light is when it goes in, enters that new medium, and then this angle doesn't equal this medium, so R is going to be the refracted angle. In Hawaii, scientists are using a telescope that uses curved mirror with a diameter 3.6 meters. What type of telescope? Well, if it's a mirror, then it's going to be a reflecting telescope. And then which of the following rows the student's observations as the teacher rotates the filter? To demonstrate the polarization of light, a teacher slowly rotates a polarizing filter 360 degrees while keeping identical polarizing filter stationary. Okay, so you're going to start off, you're going to see the light bulb really well, and as you rotate it 90 degrees, it's going to block out all of the light, and then 180 it's going to go back to normal, 270 it's going to block out the light, and then 360 it's going to go to normal. So every 90 degrees something changes, which makes C the right answer. Okay, and I can show you that one more time. This is stuff for today. So if they start off and they're lined up the same, right? 90 degrees blocks out all that light. And then I rotate another 90 degrees, you can see it again, 90 degrees blocks out. So every time you rotate it 90 degrees, it blocks out the light. And that's what you need to know. Okay, so today we're going to talk about astronomy. So things you need to know. You need to know how a spectroscope works and how it can determine composition of incandescent objects, and the conditions necessary to create a bright line, a dark line, and what that means in terms of temperature. We'll talk more about spectroscopes, how spectroscopes work. You need to know about the surface temperature of stars. You need to know Doppler shift technology, how that works. You need to know the evolution of stars, and you need to know these three terms, so black holes, white dwarfs, and neutron stars. Yeah, oh sorry, I thought there was more curriculum, that's it. Okay, so those are the key things that you need to know. So when light from a star is passed through a prism, it creates a rainbow-like pattern called a continuous spectrum. Okay, so this is why when you have a prism, sunlight shines in, you get a rainbow. However, the patterns from a star often have black gaps in them called an absorption or dark line spectrums. These gaps are due to gases absorbing specific wavelengths of light. And if you take a gas and excite it, then pass it through a prism, it'll give off bright line or emission spectrum. So these gaps can be compared to known gases and will identify as a star's composition. So I'm going to explain what all of this means here, and we can sum it up here. So what you need to know about is you need to know about how a spectroscope works. So this here is a spectroscope, and it's just something that you look through. Normally in class, I'd get you to look through this end and then line up the light on this end, but we can't do that. So what I've done is I've set up a little rig here so our camera can look through the spectroscope. Okay, so that's what we're gonna do. And then I have a light bulb down here. So a light bulb is an incandescent object, and we'll talk about that a little bit later. And then I have a hydrogen tube, right, which is a little bit different, and we'll talk about how that works. So what we're gonna do in the first situation is we're gonna do this right here. So we're gonna take white light, and to create white light, you just need a hot glowing object, and old school incandescent light bulbs do a really good job of that. So I'm gonna take white light from my light bulb, I'm gonna send it through an opening, and that's in the spectroscope. And in the spectroscope is a prism, and what we should see is we should see a continuous spectrum. So we should see the whole rainbow with no gaps. That's what we're gonna do with this first situation. Okay, so I'm gonna line up my spectroscope through here, and then I'm gonna focus my spectroscope. And what you want to be looking at is you want to look at over here, and you can see there's already some lines showing up, and that has to do with the fluorescent lights in the room, but we get these individual lines here. So I'm going to shut the lights off, and you can see those lines go away. And then what I'm going to do is I'm going to turn on my light bulb. So when I turn on my light bulb, and I adjust it so it's in the right spot, what we see in our spectroscope is we see this full rainbow here. So we see our full Roy G. Biv, red, orange, yellow, blue, green, indigo, violet. So we see these nice blue lines. So this is the opening that the light goes through, and then it goes into a prism or a diffraction grating, same sort of style, and then it breaks up into the rainbow there. So that's what we see with a light bulb. Okay, a white light. Stars will do that as well. So the other thing that we can do, instead of using white light, we can use a heated gas. So it can be any gas like hydrogen, helium, neon. Any of these heated gases will work. And what we do is we send it through the spectroscope as well. And instead of getting a continuous spectrum, we're going to get these bright lines. Okay. So instead of my light bulb, I'm going to send it through my neon light, and my neon light's filled with hydrogen, not neon. So, so I'm gonna put that in there, and I'll show you what it looks like after. So I'm gonna shut off the lights again, and I'm gonna turn on my neon light, and if I get it in the right spot, this one's a little bit harder because it's a lot thinner. Right about there. Yeah, this is good enough. So instead of getting that continuous spectrum, you can see that we get this one line here, and this other one is kind of dim. It's hard to see, but we get two bright lines here. So instead of a continuous spectrum, we get a red line and we get this blue line. There should be another line, but it's just not showing up very well. That's what we get. So I'm going to show you my setup here. I'm going to take off my diffraction grating. And this is what I have set up here. So what this is is this is a glass tube, and it's just filled with hydrogen gas. And yeah, it's just a glass tube filled with hydrogen gas. This here is just something that steps up the voltage. It's a transformer, really steps up the voltage and allows it to light up. So hydrogen always gives off this purple color of light, and it always gives off those same characteristic lines as we saw in our spectroscope. Okay, so we heated the hydrogen, ran a voltage through it, excited it, ran it through the prism, and we saw these bright lines. I should use a different color than black. Yeah, we see these bright lines. So this is called a bright line or an emission spectrum. That's what this is. So the last type of spectrum that we can see is sort of a combination of the two. So if we take white light, so our light bulb, and then we take a gas like hydrogen or helium, but it's cooled this time. So we take our light bulb, we stick our cool gas in the way, bring it through a spectroscope. What we're going to see is we're going to see the combination of both. We're going to see the full rainbow, but what's going to be missing is there's going to be dark lines this time. And those dark lines correspond exactly where those bright lines appeared. Okay, so that's a dark line absorption spectrum that we see. And you need to know how you create these three spectrums and what these three spectrums look like. So our sun is a hot, glowing object. So if you took light from the sun, so this is a sun here, and it's sending light through space, and then here is here's Earth, and then here's me on Earth, and I look at light through that with that spectroscope there. This is me holding onto the spectroscope, so I'm looking at light through the spectroscope. So what I should see is I should see a continuous spectrum, right? Because it's a hot glowing object, and any hot glowing object will give off all the different colors of light. But the sun has these gases around it. So the sun actually has an atmosphere, which seems kind of weird, but it does have an atmosphere. And in that atmosphere is oxygen, hydrogen, helium, whole bunch of different gases are around the sun, and they're a lot cooler. So as they pass through those elements, what happens is those elements take away those certain lines, right? Just like with this, if we take our white light and we shine it through hydrogen gas, the hydrogen gas takes away those lines that we see there. But with the sun, there's so many different elements that it's going to take away a bunch of different things, and what we get is we get this continuous spectrum, but we get these dark lines here. So the sun is a hot incandescent, and incandescent just means glowing, like really hot and glowing body, and gives off light at all frequencies. The cool gas outside the sun absorb these frequencies, and they're characteristic to each element. So what that means is that, okay, I see this D line here. This is neon. I know that the sun has neon in its atmosphere, right? Oh, we get this bright line here. This is sodium right here, which is cool because this allows us to take a look at any star in our galaxy, and we can take a look at it with the spectroscope, and we can see what it's composed of, and that can help us tell how old it is, because we compare it with other stars that we know more about. So these are called Fraunhofer lines, and they tell scientists what stars are made up of. So we use a spectroscope to determine the composition of a star. Okay, so excuse me. So you can see that this tells us, this should be, this isn't hydrogen, this is helium right here. So these are all the lines that are helium, this is all the lines of sodium, this is all the lines of neon. So this is a type of question that you could have. So we have an unknown gas mixture. So we have a whole bunch of different gases, and then we excite them. And we want to know what those gases are made of. Well, this is what hydrogen looks like, and hydrogen has two lines here and then a line here, which we see in our unknown gas mixture. So that means, yes, there's definitely some hydrogen in there. And then we look at, well, what's helium like? So helium is a bright line here, line here, line here. Well, none of those lines really exist, right? There's no line at the end here, and that tells us that there's no helium. And then we see a really thick line right here for sodium, and yeah, we have a thick line here, so there's probably sodium. So our unknown gas mixture looks like it has hydrogen and sodium, but it doesn't have any helium. So those are the questions that you can see. Okay, so another property that we need to know about waves is the Doppler effect, and we'll watch this video here. So that is the Doppler effect. So the Doppler effect is a change in frequency depending on how the object is moving compared to us. So as the horn was coming towards us, it sounded like it was getting higher. It's like, and then as it went past, it was, and it sounded like it was getting lower. So that's the Doppler effect. That's basically it. If you were inside of the vehicle and you were honking the horn, you wouldn't hear any of that. You'd just hear, you'd hear one constant note, and yeah. So I can explain how the Doppler effect works. So kind of like the speed of light, the speed of sound is fixed. So let's say that the speed of sound out here is about 340 meters per second. So let's go back. If I was on a bus, so this is a bus, and this is me on the bus, and let's say that the bus is moving 10 meters per second, and then I'm moving 1 meter per second, and then someone out here is clocking how fast I'm going, well, they would say that I'm moving 11 meters per second, because I'm moving with the bus, and I'm moving in the bus, so I would be going 11 meters per second, right? So whatever speed I have gets added onto that bus. But with waves, it doesn't work that way. So if this cop car is moving at 10 meters per second, and those waves have to travel 340 meters per second, you think, oh, maybe it's 350 meters per second, that's what the waves would be moving at, but it isn't. They have to move at 340 meters per second. So even though this cop car is moving in that direction, the waves have to travel that, they can't go any faster than 340 meters per second. What I sort of picture, what you can picture it as, what an analogy is picture going through the hallways of a school. I know it might be a distant memory, but say there's a whole bunch of people and they're all traveling the same speed in the hallway, right? And then you come blazing out of your class and you want to make it through there, but the hallway is jammed with all these people. So what's going to happen is you're going to get clogged up with them and you're going to move behind them. And then someone else comes out of their classroom, but no, you got to go the same speed as all the people in the classroom. And what happens is the waves start to bunch up. So in the front, you get these wave fronts that are getting closer together. And when you get smaller wavelengths, when your wavelengths are bunching together, your frequency gets higher, and that's why you hear a higher sound over here. The opposite happens on this end, right? These waves are trying to catch up to the car that's moving, and the waves end up getting stretched out. So when the waves get stretched out, right, when we get these bigger wavelengths, and a bigger wavelength means a smaller frequency, and a smaller frequency means a lower sound. So that's the Doppler effect. So a practical use for the Doppler effect is in radar guns used by police and sporting events to determine speeds. So you can use the Doppler effect to determine speeds. But what Edwin Hubble used the Doppler effect was to explain the apparent redshift of most stars. So red is lower frequency on the visible spectrum, therefore a shift to the red means the stars are moving away from us. So do I have a picture? Yes. Okay, so this is what red shift and blue shift kind of looks like. So it has to do with the spectroscopes that we are talking about. So if this is us here on Earth, and this is a star over here, and the star is moving away from us, what's going to happen is that light from the star is going to get stretched out, much like it did behind the cop car. And we know that red light is 700 nanometers, so this is red, and blue light is 400 nanometers. It's on your data book. And blue is 400 nanometers. So if we're getting longer, right, 700 is longer than 400, this means that this is a red shift. But if a star is coming towards us, right, those waves are going to get squished together, and we say it's a blue shift. But when we're talking about red and blue shift, we're not actually talking about the color of the star itself. We're talking about these spectroscope lines. So this is, if we were looking at a star at rest compared to us, this is what it would look like. But now the star up here is moving towards us, so it's moving towards us. So these lines get shifted over here, which is the blue end of our spectrum. Okay. And if a star is moving away from us, you can see that these lines get shifted over here. Every single line is just shifted over to the red end of the spectrum. So when we're talking about blue shift and red shift, we're talking about these spectroscope lines, and we're talking about which end of the spectrum they shift to. So the cool thing about these red and blue shifts is that when scientists were looking at the stars and they were looking at whether they were moving away or towards or away from us, you would think that, well, some of the stars would be moving away and some of the stars would be moving towards. But that's not what they found. They found that almost all of the stars were moving away from us. And scientists had to explain why this is happening. And an easy way to explain why this is happening is this is a balloon, and these are distances to different stars. So the only way to make all of these dots move away from each other is by blowing them up. Right? When I blow them up, they all get further away from each other. So that must mean that our universe is expanding. And that's where the idea of the Big Bang Theory came from. Well, if our universe is expanding, then it must have started from one point, which we call the Big Bang. So since all the stars are moving away from us, this means that the universe is expanding, and by calculating its speed of expansion, we can deduce its origin came from a single point, and that's the Big Bang. Okay, classification of stars. So let's talk about star color. So star color comes from the temperature. So when we talk about red and blue shift, we are not talking about star color. When we're talking about whether it's moving towards or away from us. When we're talking about star color, though, we're talking about temperature. Okay, so I can drop this down, and if I heat something as hot as a light bulb here, look at that. So what we see is this is the light given off by the object. These are all the different wavelengths. So a light bulb will give off lots of light here in the infrared, but it doesn't give off very many violet, blues, greens, or anything like that. So we can't see infrared, and it gives off mostly red. So what we'd see that light bulb glow as is it glows as a reddish sort of color. And that's when you heat something up. If you heat it up in the fire, it glows red first. But if you continue to heat something up, the different wavelengths of light that are given off change. So as I heat it up to the temperature of the sun, right, you can see that it gives off, well, lots of greens, lots of reds, lots of blues, a little bit in the ultraviolet, a little bit in the infrared, and the color that we see is white. And that's because it gives off pretty much all the colors evenly, so it glows white hot. So that's going to be our next one. But then if a star is even hotter, right, like Sirius A is a type of star, this is the peak, this is most of the light that it gives off. So it gives off lots of ultraviolet and lots of violet color, but very few reds. So it ends up glowing blue hot. So that's the colors that we see. So it'll glow red hot first, and then white hot, and then blue hot. Those would be the colors that we would see. Okay, so you can see in this chart here that a bluish star is the hottest. A white star is less hot, and a red star is the coldest. So it goes red, yellow, white, blue would be the color orders that we see. So you need to know about the birth of a star. So stars form in clouds of dust and gas, and those clouds of dust and gas are nebula, and that's what we see in this picture here. It's just random dust and gas in space, and gravity ends up collecting them together. So the gravitational attraction between the particles creates a small ball of matter, and as that ball of matter gets bigger and bigger, it draws in more and more because that gravitational field would get bigger and bigger and bigger. So as this occurs, all the pressure from all the stuff squeezing together causes the temperature to increase, and your star would begin to glow. And when it hits about 10 million degrees Celsius, if there's any hydrogen in there, it begins the process of fusion. Remember, that powers our star, our sun, is fusion, and that's when the star actually exists. Okay. So the star will glow for 5-10 billion years, and then it's going to die eventually. And the reason that it dies is because it runs out of fuel. So as the fuel in the star dwindles, it becomes a red giant star. And remember that the red has to do with the color, has to do with the temperature, and the giant they're going to talk about in the video. So eventually the fusion reaction stops, and the star collapses to form a white dwarf. Okay, so a white dwarf is from a small star. So when a small star dies, it creates a white dwarf. So what happens is we have our star, and it's turning hydrogen into helium. And then helium gets turned into heavier elements like, what's the next element there? So into things like carbon and sodium and bigger elements. And as it does that, the star gets bigger and bigger and bigger, and it becomes this red giant. But eventually it reaches iron. So iron is the most stable element, and once you reach iron, the fusion can't happen anymore, and all of a sudden all the gas is done, the star runs out of gas, and it shoots away all this excess layer stuff, and all that's left is the core. And white means that it's pretty hot still, the core, but there's no active reactions happening. It's just hot from being hot before, and then eventually you'll cool off into a brown dwarf when it after some time, because it loses the heat after a while. If the star is larger, it can create something called a neutron star. So a neutron star is just a bigger version of a white dwarf. But if a star is really, 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 really big, when it dies, all this matter sort of collapses into itself, and it creates something called a supernova, which is a massive shock wave that is sent through space. And what's going to be left behind of a super, super, super massive star is a black hole. So a black hole is only created from supermassive stars, and our sun isn't big enough. It would never create a black hole. So here's a video that goes through the life and the death of a star, and it explains it really well, and it's pretty quick. So check out this video.
Way out there in space, there's huge clouds of dust and gas, and if one of those clouds of dust and gas is massive enough, its own gravity causes it to start to collapse. So it falls in on itself, and towards the center of that cloud, it gets denser and denser, it gets hotter and hotter, and eventually the particles that the gas and the dust are made of are brought so close together that they start to stick together, they start to fuse. That's the energy source of a star. The star switches on and begins to shine.
Inside every newborn star, hydrogen atoms are fused together to make helium. This process is called fusion, and it creates the energy that powers every star. What happens to a star during the rest of its life depends on how massive it is at its birth.
A star like the Sun is in a delicate balance between gravity, which wants to make the star collapse in on itself, and the pressure that pushes outwards that comes from the energy that's been produced in these fusion reactions happening at its core. However, at some point in the future, the hydrogen runs out, and at that point, the core of the star will start to collapse in on itself under its own weight. It gets denser, it gets hotter, until a point where you can actually start to use the helium atoms themselves as the fuel for the fusion, pushing helium atoms together and making carbon and oxygen the next heavier elements in the periodic table.
As the star begins to fuse helium, it creates more energy, and that causes the outer layers of the star to expand. One day, our sun will grow so large it will swallow up the inner planets of the solar system, out as far as the Earth. It will become a red giant. For the sun, this will be the beginning of the end.
What happens is that the outer layers of the star get farther and farther from the middle. The force of gravity that they feel is getting weaker and weaker. And actually, the star loses hold of its outer atmosphere. Its outer atmosphere drifts off out into space. It expands out to become a planetary nebula. And they're some of the most beautiful objects in the universe.
Once the outer layers have drifted away, all that is left of the star is its core.
A white dwarf star is the dead remnant core of a star like the Sun at the end of its life. What's left behind is something that might weigh as much as half the mass of the Sun, but it's only about the size of the Earth. So it's an incredibly dense object, it's dead, there's no nuclear fusion going on it anymore, it's incredibly hot, but then over millions of years it will gradually cool down to become a black dwarf.
Some stars, however, are much more massive than the Sun, and they lead very different lives. They are able to fuse heavier and heavier elements inside their core. The star gets bigger and bigger. Some grow up to 1,000 times the size of our Sun, until it has fused elements all the way up to iron.
And once we've formed an iron core, there's no more energy can be got from fusion. That core collapses. The rest of the star starts to collapse in after it, but then it bounces off. There's a huge shock wave, and in just a second, bang! The outer parts of the star are blasted off into space in a huge supernova explosion. These supernova explosions are so powerful that when one of these stars explodes, it can actually outshine the whole galaxy of which it's part, a galaxy of maybe 100,000 million stars.
For these supergiant stars, all that is left is the super-dense core, known as a neutron star, an object that can have a mass greater than our Sun but be less than 20 kilometers across. But for the most massive stars of all, we think when the core collapses, the gravity is so strong, it becomes a black hole, from which not even light can escape.
So stars are actually the places in the universe where the elements are created.
After the Big Bang, our universe contained only hydrogen and helium. All the other heavier elements were therefore fused inside stars.
The amazing thing is that virtually everything you see around you was made inside a star, billions of years ago before the Sun and the planets were formed. And when that star died and blasted its guts out into space, that formed the raw materials from which our Sun, the planet Earth, and indeed ourselves were made. And actually, I think that ultimately that's one of the major reasons why I think understanding stars is crucial, because it's actually telling us where we came from.
Okay, so that's it, and I'll attach an assignment, and if you have any questions, shoot me an email. Let's go through the assignment and those sample diploma questions. So for each of the following spectra, describe a possible source. So continuous spectrum is glowing, hot, or incandescent object. Absorption spectrum are a dark line. So you have your white light, and it passes through a cooler gas. Okay, and then the bright line spectrum is an excited. So to excite it, you can make it hot or run voltage through a gas. Okay, show the main steps of an evolution of stars like the Sun. So it starts off as a nebula, which is a collection of dust and gas, and then they collect all together, and then you get a star, right? And then when a star like ours, which is a low mass star, dies, depending on its mass, it either turns into a white dwarf, or a neutron star. Okay, and then in between there, as it's dying, it turns into a red giant as well. If it was a bigger star, it'd be the same. So starts off as a nebula, and then it's a star, and then it would get bigger, it'd turn into a red giant, and then it has a supernova where it explodes, and then it turns into a black hole. That's if it's a bigger star. That's what it would turn into. Okay. The following spectra was, you guys get it in color. Normally in the workbooks you don't get it in color. So the following spectra was produced by a source that was stationary. A and B were moving. So you can see that these two lines here were shifted over to the blue end of the spectrum. So this is coming towards. And then these two lines are shifted over here to the red end of the spectrum. So this is going away. Okay. So this is a red shift, and this is a blue shift. So that's for A, and then for B, the source of the spectrum is moving towards the observer, away from the observer, did that already, and determine which of the two spectra was produced by the faster moving object. So it's faster if it's moving over more, right? So this one is moved over quite a bit, and then this one is just moved over a little bit. So the blue shift would be moving faster because those lines are shifted over more. Okay, so that's the assignment. And then now we'll do the sample diploma questions. Make sure you try them on your own before I go through them. Okay, so for this one, it's saying match the sections of the diagram, use each number only once. So for 1, so you can see that we're creating this bright line spectrum. So 1 is going to be a hot gas. And then we create this dark line spectrum. So 3 is going to be a cool gas. 2 is an emission spectrum, and then 4 is an absorption spectrum. So bright line is emission, dark line is absorption. It's absorbing those dark lines. 16, when compared to the electromagnetic radiation emitted from a stationary source, the waves of light from a light source that is moving away will have, so moving away is a red shift, which means that our wavelength is getting bigger and our frequency is smaller. So it's going to have a decreased frequency and an increased wavelength. D is the correct answer. And then 17, compared with the standard hydrogen spectrum shown above, the hydrogen spectrum of a celestial body is red-shifted or blue-shifted. So for this one, this is a standard hydrogen spectrum, and this is a celestial body, so it looks like these lines are moved over here, which is the blue end of the spectrum, so they look like they're blue-shifted, which means it's moving toward an astronomer, C. Okay, and then this last one here, which of the following rows identifies the most likely end product of each of the 2 star sequences? So we have a low mass here. Yeah, we have a low mass, so that's probably going to become a white dwarf. And then we have a high mass and a supernova, which means it's going to become a black hole. So 18 is A. Okay, that is it. If you have any questions, let me know, and you get your quiz tomorrow.